So I wanted to go through this chapter one, and just to go over again what we covered in class. Um, what you should get out of this chapter is really sort of an introduction to a little bit to science and chemistry, just some basic topics that we're going to be using over the semester. And like I said in class, the point of this course is to really give an overview of chemistry and how we use it in different aspects. And that's the flavor we're trying to get, but we have to start off with some basic principles. So, the first few chapters, we're going to be doing that. And I'll always try to add in something to make it more relevant, aside from just giving you, what you would get out of a normal chemistry class in terms of just straight basics. So this chapter is sort of a beginning of that. So let me just get this on view. There we go. Okay, so I started off by sort of setting the stage to let you know how much chemistry is actually part of our life, even if you're not really thinking about it. And the reason I like this image here is that you can really see how many, and there's more, but this is a good snapshot of where chemistry it has an influence in your everyday life. And some things you might think of more intuitively and other things not so much. In class, it's sort of brought in even meteorology, because that's, for me, I don't always think of that as being chemistry, but it is. And why is that? And that's because chemistry is the study of matter and its changes, and matter being anything that both has mass and volume. So anytime matter or anything with mass and volume is changing in some way, you're dealing with chemistry. And that's that was sort of the point here. Then the next idea is science. Right, so a lot of people confuse the idea of science and tech, saying that they can use those terms interchangeably, but actually that's not quite the case, right? So most of the time when we're dealing with science, most people are dealing with some sort of application of the science, which we'll talk about in a few minutes. So that's really technology, but science really is, and what I was saying in class is that originally science really wasn't doing experiments. It was looking at the world and making philosophizing about it, or speculating about why it's behaving the way it is. And at the very beginning, our understanding of the world and how it worked was very limited. And that was sort of the point here. And this is why, and I had said, my terminal degree is a PhD, and what that stands for is Doctorate of Philosophy. So a scientist who has a PhD is actually a philosopher. And the way it works, if you go that far, like I did, is just you get to be really good at something, and you so good at it that you can philosophize about it, and you can sit in a room and discuss the nuances of it based upon your understanding of it. And that's what PhDs do. Aside from just doing experiments, when you just do experiments, you get to the point where you know enough about a subject that you're an expert in it, and that was sort of the point. Okay, but the next point I made is that you can use technology and not really understand the science behind it. Okay, so I mean, not all of us, if you think about our cell phones, a lot of us really don't know how that electricity is doing what it's doing inside the phone, but we still can use the phone, right? And at a more rudimentary level, I was talking about fire, right? We were using fire long before we really knew what fire was. So that's sort of the difference between that. But usually now, since our understanding of the natural world, and we have a lot to learn, by no means am I saying we've got it, but we have enough now that we can already sort of try to adapt our science to get to our tech. So that's why we use these things interchangeably now. So where did all of this start? Well, it started with the alchemists, and those were the original types of scientists. Even though they came after the philosophers, right? But the alchemists, they would try to use a little bit of everything to try and make things happen. So there was a little bit of sleight of hand going on there. In my notes, I talk about the philosopher's stone and the elixir for eternal life. I mean, those are the alchemists. But really, they were trying to explain. They were the first ones trying to use nature or what's around them and make things happen. Okay, so that's why sort of alchemy was sort of the first science by the way we normally think of it. But it wasn't really until the 1800s where we had this explosion of knowledge and the way we used and our understanding of the world was really expanding. That's not to say it wasn't building before that. You'll even see in this course, I'll talk about some scientists from the 1700s, and I think even the very first really experimentalists were using the scientific method as I'm about to go over it. I think he was in the 1700s. I don't think it was 1800s. I can't remember the year offhand right now. But in terms of, understanding nature, really, it really exploded in the 1800s. And a lot of this, the magical end was kind of like, the Middle Ages, where we call the Dark Ages kind of thing, where we didn't understand much. But I brought this in here because this was sort of the original periodic table. And you can look down here, the design was by Aristotle. And if you look at what you're looking at here, what you're looking at, but you can even see the zodiac symbols here. You can see the seasons, right? Here you've got elements, but what are you talking about? Well, you got fire, water, air, right? So it's kind of not what we would normally think of. And I think what you will find in here, I think there's oxygen, right? So there's something, and I believe gold is in here somewhere, but then we also have, female and, things like this, male, these symbols here, but you notice that's copper and that's iron, but this is now known as the male symbol, and this is the female symbol. But so you can sort of see how things were, how things evolve. So there's a few elements in here that we think of, but a lot of it is not. So that's sort of my point. Look at here: day, night, hour, pound, ounce. So you see what I mean? Okay. Now, modern science, the way we think about it, science has two ideas. First of all, it's knowledge about the natural world, like I've expressed, but it's also become known to be a process. And my point in the previous slides to let you know that it wasn't always a process. Okay, so the ability to acquire that knowledge has been divided into certain steps, which we call the scientific method. And every scientist uses the scientific method, although the way they might use it is a little bit different. Okay, so you have to understand that's a little bit fluid. Okay, and indeed, when we're in lab, I told you from the get-go, I've never run a lot of these labs. Some of them I have, but a lot of them I haven't run. So, it even happened in our first lab. Something happened. I think it was Michael asked me a question, and I said, well, I'm going to tell you why I think this. This is what I think, and this is why. And the point of me doing this is to dispense, my expertise on how I try and reason through here. But we'll work through the labs and we'll see what happens. Okay, and we'll learn something in the process. All right, so don't expect everything is going to be perfect in this class, but we're gonna learn from something, whatever we're doing. All right. So what are these 5 steps? And you've probably heard about these before. All right. So observe and generalize. So make observations. And sometimes it used to be that you would say, ask a question. Right. So I'm going to use my plant example. So it could be like, what do I need to make my plant grow? Right? So you're looking around and you're going to observe and you're going to make generalizations about that, right? The example here, every winter in the past it was colder than the summer, so winter will always be colder than summer, at least in the northern hemisphere, right? So we can think of it that way. I was watching a video the other day of a YouTuber I like to watch. He's in Australia, and at Christmas time there, they go to the beach. So it's different down there, but from our perspective, that's what we can go with. All right. So then what do? Well, we formulated a hypothesis, and this is a tentative explanation, right? So if I said, well, what do I need to make my plant grow? And then you look around and you think, well, and notice that there's water, but, there's hardly any plant growth, or the grass burns out in the summer when we don't get any rain. So I can say, okay, my hypothesis is that plants need water to grow. All right. That would be a hypothesis. All right. And this would be based on what you've observed. All right. Then the next idea, okay, since we propose the answer to the question, my question is, how does it grow? What do I need? But the important, the workable part here is it has to be testable and falsifiable. All right. So I said in class, a lot of people think, oh, if you're a scientist, you can't believe in, you don't have any religion. Well, indeed, a lot of scientists are atheists. That's true. But there's also a lot of scientists that happen to believe in some form of religion. All right. Because especially for me, like I'll share with you, yes, I do. I actually happen to be Catholic. Right. So, but to me, you can't test religion. There's no way of, it's not falsifiable and it's not testable. So to me, science is something different than religion. That's something that, helps me sleep at night, and sets the guide for the way I live my life. It has nothing to do with science. All right. So that's different. You can't test it. You can't make it false. And that's why you need any attempt to do that. And I think I also used in this example that show Ghost Hunters. Some people remember that show. I don't know if they make it anymore. I used to watch it because I thought it was funny. But you can't really test if ghosts are there, right? So that's the other thing. But if you've ever watched the show, you'll know that they do try to put some science in there, but it's really not something you can prove false. And part of the reason is our ability to look for patterns. And we're going to talk about that as well. Okay. So the next thing isn't the experiment. The next thing you have to make is a prediction. And the prediction is going to form step 4, which is the hypothesis, the experiment, right? So it's going to test the hypothesis, and it's usually phrased as an if-then. It doesn't have to be, but it can be. So if I'm going with my plants and water, and I say, well, I think my plants need water. So if my plants need water, then if I add water, they'll grow, right? So that's sort of the idea that you have here. So it's an if-then. I know I used 2 ifs there, but so if water helps my plants, then I will see them grow. Let's put it that way. Okay, and that's based on some deductive reasoning, based on some facts that I've already accumulated. Okay. Now, whatever you do, this has to be very well-defined, measurable, and controllable. And that's sort of the thing that I brought up here. Here's our experiment. We've got 3 plants. We're testing water. So in one case, we're not giving any water because 0, right? It's always good to start with 0. Another one, 20 mils or 40 mils of water. Now, in terms of controllable, right, what are we talking about? Well, the important thing here is, first of all, we're testing our prediction. Is water helping the plant to grow? Operably, this has to be a very simple, well-defined and executed experiment. And I was sort of saying, if you've ever tried to reason through something, the more variables you introduce, the more difficult it will be to arrive at a conclusion. So the idea is really to make it simple. So here in this experiment, all that's being tested is the amount of water in the plant growth. So this is where I bring up a controlled experiment. And this is where students get confused. You controlled variables. So the controlled variable is going to be anything else that it could affect, in this case, my plant growth, but I don't want to test that, right? So we were talking about in class, well, the quality of the soil, the temperature, the amount of light. Those are usually, light and temperature are usually the first 2 things that students come up with, okay? So if I'm only going to test water and I want to see the effect of water, that means the rest of them have to be the same for each plant, okay? That doesn't mean I'm going to grow them in the dark, right? But they have to be in a place where they're going to get the same amount of light every day, right? Or for the length of my experiment. They have to be the same type of soil. I can't run out of a bag of soil and then think that I can use a different bag for my 3rd plant. So I have to plan my experiment so that I'm going to use the same bag of soil. Or if I find I need 2 bags of soil, before I do my experiment, I'm going to mix those bags of soil together to get more soil so that each plant is sitting in the same quality of soil, right? So that's how you have to sort of think about that. Okay, so that's the controlled experiment. But now comes the test, and there's the 2 variables. The independent one is the one you're investigating. So in this case, we're investigating the amount of water. So yes, the amount of water is going to change, but that's the one I'm investigating, is the effect of water on my plant, so that's the independent one. The dependent variable is how I'm going to detect that change. So what am I going to measure that's going to allow me to detect that change? And usually people go with height because that's clearly the most obvious way of doing that. Unless you're dealing with a dwarf shrub and you're not going to grow anymore, that might be harder. So then you have to think of, well, the color of my plant, the quality of my root system, the thickness of my stem. So this is when you really have to think about it. If you're growing plants from seeds, definitely you can use height. That's really easy then, right? So this is what we're looking at in terms of our experiment. Now, the last thing is, have you supported or falsified your hypothesis? You can't prove your hypothesis true. Okay, and this is what I said why. Because even if your experiment agrees with what you hypothesized, it's only within the parameters of the experiment that you've just run. So the reason I choose plant growth and water is because we all know that you can overwater your plants. Okay, so if you choose a window where you're using too much water, the height is going to droop, right? Your plants are going to die. So then you might come away with the conclusion that, you know, water is bad for plants, right? Or if you just look at the part where the plant is growing, you say, okay, water is good for plants, right? So if you think of it in that terms, I know that's really simplistic because our knowledge of plants has expanded past that, okay? But understand that you're only correct within that framework of that experiment, okay? However you treat that hypothesis. So the point then is, what do we do? Well, we have to keep doing experiments. You learn something with each iteration here. You observe, generalize, formulate hypothesis, test it, and then you keep going. And then from that, you got some more things. Well, what about if I give it more water? What if I change the soil? What if I change the temperature? So each time you're going to learn a little bit more, and your questions are going to get more and more sophisticated with each time you do this. Okay. Now, the other thing then is that scientists are obligated to make their findings known. Okay, it's sometimes when they talk about looking at the scientific method, they'll use the flashlight and the battery idea. And that's to show you that everybody does experiments, right? If your flashlight isn't working, you're going to test several things. Is my bulb broken? Is it my battery, right? Is there something else wrong with my flashlight? But everybody will do experiments, and that's why they use that. But it's only scientists that are obligated to publish those findings. If you figured out that you need a new battery in your flashlight, you don't need to publish that, right? But if I'm doing an experiment, the effect of taurine as a stimulant, and I want to further the use of taurine for Parkinson's patients, I should let people know what my findings are. Okay, so this is where as a scientist, I'm obligated to share my knowledge with every other scientist. Okay, and the reason is that there's no way we can get further in understanding of nature if we don't share our information, because there's no way that one scientist can do all of it. And then if it comes down to that, if you're a scientist and just say you are doing all of it, what's the point if you're not sharing that knowledge with anybody? Okay, so this is where you're obligated to publish. And my point here is that it's not easy to publish. Okay, so there's a lot of checks and balances. There's scientists that are going to review other scientists' papers that have an understanding of that. I actually did that over Christmas break. Not that I thought, oh, great, I want to spend a whole day looking at somebody else's science. But as a scientist, I want someone else to review my paper so I can get it published and give me feedback. Then I have to do the same thing for other scientists. So they selected me because of my expertise. And then I used my knowledge to help look at this paper and make a recommendation. Should it be published, or should they go back and do some more work? Okay, and in my case, it was the latter. I didn't think they needed more experiments, but they needed to clarify their findings. So there's a lot of push and pull that goes here, and sometimes you submit to a journal that's not even the right one. A journal can say this study is not the kind of paper that we're going to publish, so you have to go find another journal. And the other thing that I mentioned in class was that it's not free. Okay, so you pay. So scientists are not making money out of this. The only kickback you get as a scientist after you publish is that you've shared your information, yes. But it helps you grow in your field, and it might make it easier for you to get a grant. All right, so that's kind of the thing where it goes here. So you build your reputation. Now, when it comes to that, though, most people don't read peer-reviewed journals. All right, you're not going to have a copy, or most people aren't going to have a copy of here, I don't know, ASCB. This is going to be the American Society for Biological Chemistry, I'm going to guess, sitting on your coffee table. So most people aren't going to read that. But it's important for everyone to understand the nature of what's going on in science. So what do we do? Well, this is my table here. So you got your peer-reviewed stuff at the top, which is the stuff that most people don't read. Even I don't read every type of journal, because I'm very specialized. I mentioned in class I'm a biochemist, and I said I'm a very biochemist, right? But when it comes to physics, right? So there's no way that I'm going to read cosmology and find out what's happening with black holes looking at this. I can try, but I'm not going to understand much. So, that's when we have this tier system, and it's going to depend on how deep you're going to get. And down here, though, at the end, you have to, and I said in class, follow the money, because what ends up happening is that personal interest groups or trades or whatever it is, they have an agenda. That's the word I can think of in class. They have an agenda. And that becomes even more apparent when you deal with the internet and special interest groups. There's no accountability. They can pick and choose their information and disseminate it the way they want and take the slant that they want in order to push their agenda. And that's something that you have to really be a self-doubter. And then we're going to talk about where that comes from. And that's this, being a critical thinker. Always be skeptical. Don't just believe someone because, you know, they're your aunt or whoever. You know, you have to be skeptical. Ask the questions, ask the hard questions. Learn to read the data if it's in a publication form. Look at where the data is coming from, right? Look and see, you know, are you getting the full thing? Stats are important. If your sample size is 1, you know that that's not really scientific, okay? And that's where we come to here, this idea of evidence or anecdote, right? And it's important to stress here that science really doesn't care what you want it to be true. There's no sides here. It's whatever the data is supporting. That's what it is, okay? And whether you're happy about it or not, it doesn't matter. You're just going to have to deal with it. That's when you have to, you know, be the adult and say, okay, that's not the way I wish the world was, but that's the way it is. So what am I going to do about it? All right. So this is where this comes from. So an anecdote is sort of like a personal reflection. That'd be like my aunt. She always used to, you know, have anecdotes to tell me. She said, "Oh, don't rock the boat." That was her favorite one, and I always did the opposite. I'm a boat rocker, but she'd say, "Don't rock the boat," right? But you know, you could also say, you know, I grew up drinking beetroot juice, and it's going to solve all your woes, right? So, you know, that's an anecdote. You say, well, how many people did that, and what's your evidence, right? So you have to really reflect on that. Okay. Are you dealing with a fact or conclusion, right? So like I just said, one experiment doesn't always allow you to make a complete conclusion. You might be able to make a conclusion within the framework of your experiment, but if you really want to know for sure, is water always the best thing for your plants? It's going to depend on your plant, right? I always overwater my orchids. So, I mean, the conclusion might be a little bit more specific, and you have to look at where it's coming from. So you have to think, is this a fact or is it a conclusion? And here, the differences between correlation and causation. I could talk to you all day about that. Okay, so my example was this one, right? So we'll take it. I'm going into the autism direction. All right. If I said to you, like I said in class, if you look, the sales of organic food have been matching the cases of autism for the last 30 years. Okay, so and then I said, do you think that organic food is causing autism? And most people pretty much said, no, I don't think that. Well, why? Why? Because it's organic food. It should be fine, right? Because you trust organic food, right? You know where it's grown. You think you do. It's not that simple, but you know, so you're pretty, you know, so here you could say, oh, this correlation, that's not a causation, right? But you know where I'm going with this, right? So vaccines, right? So there was and I could talk again on ad nauseum why that guy did that, but there was a paper that was since retracted because it was proven that it wasn't correct and it was massaged. That vaccines, is a preservative based on mercury called thimerosal was placed in the vaccine, and this guy said, okay, this is what's causing autism. And this has caused so much damage across the planet that it is ridiculous. All right, there has never been another paper ever that has ever shown this. Thimerosal has even been removed from vaccines, and we're still getting an increased incidence of autism. All right, so this is really important. Okay, so just because there was a correlation, because this guy massaged his data, he wanted to make a statement, and this is the thing. And I asked you in class, why would a scientist do that? Why would a scientist falsify their results? Okay, and you know, we talked in class about a lot of different reasons that a scientist might do this. Okay, but look at the damage it's caused, right? And the amount of money that has gone into checking vaccines to make sure that they're not the cause of autism has been, to me, you know, where we could have taken all that money and invested it in helping finding a cure for autism. That's how I feel about it now. It's just gotten to the point where it's ridiculous. And I feel pretty strongly about that because I hate it when things are just wasted. But this is a classic case that people need to understand that correlation and causation do not mean the same thing. And it's so much easier for someone to suspect something that they don't know what's in that mixture. And of course, that might be the problem. And we're going for conspiracy theories. And believe me, I have my own kid, and I would never have given vaccines if I thought in any inclination that I might be giving her autism from that. All right. So you're forgetting scientists have families too. All right. So, anyways, correlation does not mean causation. All right. So how do we get around this? And I kind of saw this. This one is actually in your book. I teach this as well for the 105 class. It's not in that book, but I think it's a really nice way of thinking about it. So flares. So is it falsifiable? So if you look at the data and the conclusions and the statements that are being made, if they're not falsifiable, just forget about it. All right. You're dealing with someone's opinion. Logic. Is it logical? Your logic can get you a long way. All right. If something's not logical, if it doesn't sit right with you, all right, if you have to ask yourself that. Is it reproducible? Has it only been seen once, or has it been seen thousands of times? That's the other thing. Is it replicability? All right. The other one is sufficiency. This one's a harder one, so I'm just going to talk about that a little bit. If you're making an extraordinary claim, all right, if you're making an extraordinary claim, the evidence better be pretty extraordinary too, all right? And I think that if we applied flares when it came to the vaccination thing, we would have gotten to the point that, all right, let's look at this a little bit better because nobody else is finding this kind of data. Why is that? Okay, so I think that would have solved a huge problem. All right, so think about, is it an anecdote, is it evidence, or is it some sort of weird experiment that wasn't run properly? And especially with something that profound. All right, so I'm just wondering if you guys know which book this is from, because if you do, you're really cool. So passion rules reason. I really love that because it's really true. So don't fall for that. All right, we all are passionate about something, but it's the grown-ups that understand that just because we're passionate doesn't mean that we have to have that. All right. Now, building on that, so the difference between basic and applied research. Okay, so basic research, it's really done, this is where you're philosophizing. You're trying to understand the way the world is working. It's driven by curiosity, all right? Its objective isn't to make money, okay? It's not gonna have, you're not doing it because you wanna have a commercial advantage. And this is sort of the problem right now, because in order to get money to do research, you always seem to have or foresee an application. And that makes it really challenging because in order to make real discoveries, we have to be able to do some basic science too, okay? But now we're very, very focused on this end. If we can't apply it, then why should we spend money on it? And as an example, I brought forward the idea of MRIs, all right? And the reason I like this one is I was actually at an institution that was actually developing this, and I still remember when I started graduate school, they were really trying to understand what was happening, and it wasn't evident right away that this could be used to image someone's internal tissues. All right, at the beginning, it was physicists, playing around with atoms, and they noticed that these guys spin in a magnetic field. Right? In a magnetic field, you can get these all guys to align their spin, all right? And then if you apply radio frequencies, some of them are going to relax, or they're going to get aligned in with the other ones. And then if you remove the frequency, they're going to relax. We call them, I used to work with some radiologists, so they explain this, they call it relaxation. So these ones, once you turn off the frequency, some of these guys are going to relax. And when they do that, they give off energy. Now, the amount of energy they give off is going to be attenuated or changed depending on what they're near to. So if you're, let's say that this is a hydrogen in a water molecule and you're in the blood and now you're close to iron, the way you're going to relax is going to be different than if you're a water molecule in some soft tissue in the brain. And this is going to send off a different signal, and they could realize it could start taking pictures of the molecules. And then this was then applied to using MRI. All right, so the point here isn't that you're going to remember how this all works, but if they didn't ask these basic questions about atoms, having no idea at the time that you could use it for imaging, then we would never have MRI, right? And MRI is such a powerful technique. All right, so this is sort of, an example of what I was trying to get at here, okay? Now, so the other little thing, I'm sort of going away from what is science and why we're doing it. We're going into, basics of chemistry. And when we're looking at chemistry, I said it's a study of matter and its changes, but what kind of changes do we have? We have two kinds. We've got physical changes and we've got chemical changes, all right? So physical changes, here you're not changing the substance, you're just changing its behavior. Okay, so water into ice, and then, or water into water vapor. Okay, but it's still water. A chemical change is that you're actually making something new. So the example here, you're starting off with hydrogen peroxide and you're breaking that down into oxygen and water, right? Or hydrogen and water, sorry, hydrogen and water. So that is actually a chemical change. You're starting off with hydrogen peroxide and you're ending up with two different types of molecules. So that's a chemical change. And this is not something that you can change, right? It's not easy to go back from water to hydrogen peroxide. You have to do a chemical reaction, okay? Here, this is easily to go back and forth, a physical change, because you're not making a new substance, okay? Then with that, in your standard definition, solid, liquid, and gas, right? So a solid, it has its regular shape and volume. A liquid has its regular volume, but its shape can take that of its container. Whereas a gas is free, right? It maintains neither shape nor volume, all right? And we're going to be talking about all of these in this class. The next idea is the difference between substances and mixtures. So substances we consider sort of, a uniform molecular bound structure. So when you're talking about an element, this an element cannot be broken down to anything smaller. It's the smallest particles. Yes, we can break atoms, but when we're not talking about nuclear breaking down things like that right now, we're just, the element is the simplest one. The atom is the smallest particle in an element. And when we're talking about a compound, it's a mixture of two or more elements, but they're bounded together, right? So the two or more elements are chemically bonded, right? Whereas a mixture, you can take elements and you can take compounds and you can make mixtures, right? So a homogeneous mixture is going to be uniform, but you can separate it, and we're going to do that in lab, right? A heterogeneous mixture is one that isn't uniform, all right? So we're going to be doing the heterogeneous mixture in lab, all right? The other thing that we have to make note of is the metric system. I don't spend a lot of time on it in this class, but you need to be aware of it because we're going to use it, and I'm going to be asking you some questions on the homework where you're going to switch units. So why do we do that? Well, metric, or the system international, it's French, the international system units of measurement, is used by pretty much everyone on the planet, except for the countries that you see here in red, so the United States, Liberia, and Burma. Everybody else uses metric, okay? So it's really the way things are done, and we need to use that in lab as well. So when you're answering questions, it's going to be metric, all right? So how does metric work? I'm sure you've done this before, and please watch this video. It's a nice little review on it. But basically, when it comes to the metric system, there's a standard unit, and everything is based on that standard unit. So for length, it's a meter, mass is the gram, volume is liter, time is a second, temperature is actually Kelvin, in common usage would be centigrade. I don't have that here because we're mostly going to be doing this. But you need to be able to convert between these. I do want you to learn your prefixes. So basically what we're dealing with is how many times. So instead of using huge numbers of zeros or huge numbers of decimal points, what we do is we just give it a different a prefix. So if you see the prefix kilo, that's going to be 1,000 times that base unit. Okay, so a kilogram is 1,000 of these grams, or a kilometer is 1,000 meters. You could just write 1,000 meters, but it's a shorthand. So if you say kilo, you already know that there's 3 zeros after whatever number of meters you have. Okay, milli is the opposite. Okay, so that would be a thousandth of that. So instead of putting all of those little zeros in front, we'll just put milli in front, and it simplifies the whole thing. Okay, so then there's the conversions, and I'm going to give you a little mnemonic, and there's going to be homework questions to practice. Please do that. All right, this is really good for life. All right, so you should be able to do this. So basically, if you're converting to a smaller unit, you're going to move the decimal place to the right. If you're using a larger unit, you're going to move it to the left. Okay. Now, here's a little mnemonic. So it's King Henry died unusually is your units. Drinking chocolate milk, so you're starting at kilo, hecto, deca. Sometimes you're going to see this with a K. Okay, deca. Then your unit, and then deci, centi, and milla, or milli. So deca, trying to differentiate between this, just remember a decade is 10 years. It's not a tenth of a year, it's 10 years. So that will help you remember that the deca is the bigger one, okay? And these are the ones that we're going to use mostly in class. The other one that you might see is micro, because micro would be a millionth of it. So, you know, that's what we use for your microscopy. The other one that you'll see in the news and stuff would be nano, right? Like nanotechnology. What are we talking about? When we're talking about things that are on the billionth of a meter or billionth of a gram, we're dealing with that. Mega millions, right? So that's the other one you might see, that prefix. So that's a million times a base unit, right? So $1 million, so that's mega, all right? That will help you remember. Giga is a billion, all right? But most of the time we're going to be dealing with, you know, this mnemonic here. King Henry died unusually drinking chocolate milk. If you can remember micro, that's going to be great for you, okay? So give that some practice in the homework, all right? There's really nothing I can do other, you got to practice. Now, so length commonly measured in meters. So here you've got your other standards. So centimeter, you know, there's 100 cents in a dollar, so there's 100 centimeters in a meter, and then millimeters. Okay, so there's, you know, 10 millimeters to a centimeter, or 1,000 millimeters to a meter. Okay, so try to remember that one. Volume is measured in liters. This comes back to lab. I was hoping I was going to be done this before our lab, but because of the snow day, we didn't. But volume by displacement. So remember what that is. If you put something heavy, this is what you use for unusual shaped objects. So when we were talking in lab about the king's crown, that's probably the best way to get the volume. So measure the volume of water before you put the crown in, and then see what the volume is afterwards. The difference is going to be the volume of the crown. And that you can then use to calculate density, which I'll talk about in a sec. Another useful thing to know, and this works well for pure water, is that 1 milliliter is 1 cubic centimeter, or 1 cc. This is why when you go to the doctor's office and they give you a vaccine, it's measured in cc's, cubic centimeters, but it's the same thing, mils. So it's interchangeable, especially for distilled water, and most of these vaccines are made up in water. So the other thing in lab, when you're measuring volumes, we didn't do that yet. Remember, you got your meniscus, so that's your upward crawling of the water. That's property of water. It's sticky, it likes to climb up things. So you need to measure from the bottom of the curve, all right? So try to remember that when we're doing that in lab. Nothing that we're doing in this lab is going to, you know, really suffer if you forget. That's the nice thing about this chem lab. But it's a nice thing to have in practice. All right. So then density. So remember, density is mass over volume. All right. So needed to introduce this for lab. So mass in grams over volume can be cubic centimeters. It could be in millimeters. All right. It depends. Because sometimes if you're dealing with a solid cube, you can use a formula to get the volume. Okay. But remember that this cubic centimeter is going to work to mils. All right. So there you go. Now, the difference between mass and weight, right? So mass is the amount of matter in an object, so that's always going to be the same. But your weight is the force of the gravity on mass. So your weight is going to change depending on where you're at, all right? So if you go to the moon, which is smaller than the Earth, you can have less pull of gravity, so your weight is going to be less. All right, but your mass is still going to be the same. So that's really important. We use those terms interchangeably because we don't go anywhere. Very few of us have the privilege of going into space, so don't really worry about it. But this is the standard definition. Now, the next idea, we don't deal with this too much in this class, but I want you to understand something in terms of energy, because we're going to be talking about green chemistry and trying to save energy. So there's different types of energy, and energy in general is this definition: the capacity to do work. all right? But that capacity can be active or could be stored. So the stored energy is potential. It's not being used yet, okay? So I use the same slide in my 105 class because I deal with muscle, but if you're looking at Michael Phelps, you know that this guy's got a lot of power when he goes in the pool, right? So when he's on the block, all of that power is stored up in his muscles. So in that point, it's potential energy, right? And as soon as he hits that water, even after just moving off the block, that energy, if you ever watched videos of this guy even jumping off the block, my daughter's into swim, so we watch Michael Phelps for fun sometimes. There's lots of videos. So all of a sudden that potential energy is going to be released into the energy of motion, and that's called kinetic energy. Okay, and I'm introducing this idea because I'm going to talk a little bit about food later on in the course, and we talk about calories. So I want you to understand where this comes from. We're going to come back to it way at the end of the course, all right? So one way of measuring energy is in this unit called the joule, all right? We're not going to measure it, but I want you to see how this converts to calories, because I need you to understand, or I'd like you to understand, that the calories that you're eating in your food is the reason they're called calories. This is a measurement of energy in that food. Okay, so a joule, all right, is the standard way that the SI unit for energy is the joule. All right, and that is going to give you how much work can be done by that energy. Okay, now, when we're talking about different forms of energy, and I'm going to come back to this joule in a sec, okay, you have heat and you have temperature, right? So when you're working out and you're using that kinetic energy, it's not efficient, right? So you know when you work out, you start to sweat, right? So all of that energy that's being released is being released as heat. Okay, so we can think of heat as energy that's being moved, right? It's coming off of your hot body and it's going out into the atmosphere, all right? So that's energy on the move, but temperature is different. That's the average amount of kinetic energy, the movement of the atoms in an object, so how hot or cold it is. So what you're measuring with a thermometer is the movement of those molecules in that substance. It's slightly different, okay? And that's not energy on the move. That's just really how much are the molecules moving in this. In when we do I do yeah I do yeah. So in when we're talking about science, okay, remember I said that Celsius and Kelvin is really the unit for science. We use it interchangeably with Celsius because that's more practical. Things freeze at 0, makes logical sense. They boil at 100. Right? But when we're really talking about science and we're thinking about this temperature idea, right? How much of those molecules are moving? So we have a temperature, all right, on the Kelvin scale where molecular motion stops, and that's called absolute 0, all right? So if you are a scientist that's dealing with the movement of matter, you're going to measure things in Kelvin, because at 0, that's when things stop moving. All right, so this is why this is important, understanding the difference between heat and temperature, right? So if you see something or report saying, oh, it's absolute 0, it's pretty damn cold. That means that nothing is moving. In terms of what you guys might be familiar with, that's like, 460 degrees, below 0 on the Fahrenheit scale. And in Celsius, it's minus 273, okay? So it's pretty dang cold, all right? So that's sort of where that comes in, and hopefully you'll understand that now if you see somebody saying it's absolute 0. What does that mean, okay? Now, coming back to the food idea. Now, when you have your food and it has calories, really that's calories with a capital C. What that actually is 1,000 kilocalories. All right, so kilocalories is coming closer to what we're looking at in terms of energy. So how much energy is that? Well, 1 calorie being 1,000 kilocalories is actually 4,284 joules. All right, so that's the kinetic energy that's stored up in that food. Okay, and I think I wrote down somewhere here. It's 1 calorie is the amount that's required to raise the temperature of water by 1 degree. I thought I wrote that down somewhere. Maybe I didn't, but anyhow. So very often what they'll do is to get the number of calories in a food, they'll put it in something called a bomb calorimeter and then ignite it. And the amount of energy that comes off from this burning sample is a measurement of how many calories are in there. Okay. And in this video here, I showed you guys the burning of the gummy bear. There's a lot of calories in a gummy bear, right? And you can see that energy being released when it's been ignited in this video. So that's what, that's what I was trying to get at there. And then other than that, that's it for this chapter. It's really a good overview and stuff. So where did I put that? Yeah, it's in my notes. A calorie is the amount of energy needed to raise the temperature of water, temperature of 1 gram of water by 1 degree Celsius. All right, so that's where it comes in terms of that bomb calorimeter. All right. Okay, so hopefully with this video and my notes, you'll be fine. And like I said, I really don't expect you guys to just listen to me and get it right away. But hopefully that helps. All right. And as always, any questions, come and ask me. I can't promise you that I'm going to have all the answers, but I'm definitely going to try.